Hello everyone and welcome to another video provided by SVSU's online tutoring. My name is Joel and today we will be looking at section 7.1 radical and rational exponents, and the topic this time is radicals and calculators. So throughout this entire section we've just been introducing more and more definitions, right? We've seen the very basic definition for, let me switch colors here, for some number a equal to b raised to the nth power. And then as we move forward, we've just continued along using this definition, but we've been writing it in different ways, like this one right here. So the principal nth root of a number, if n is some positive integer, it's the index of the radical, okay? The index of the radical. And then if n is equal to 2, we just write it as the square root of a instead, rather than the second root of a. This is just a type of formality type of deal that you see that's rather common in mathematics. We've also looked at inverse properties of nth powers and roots. So if we have if our index for our radical is also equal to the power, then they cancel each other out and we just end up with a again, okay? And you can see an example over here where we have the second root, okay? So we're taking the square root of 5 raised to the second power. Well, they cancel each other out. And we just get 5 again, right? And then if n is odd, okay, where the ends are equal to each other, they again cancel each other out. So this cubic root cancels with the cube, and we just get 5. And then if n is even, we end up with the absolute value of a. Okay, so the square root here, they cancel each other out, okay, with the square, and then we take the absolute value of a. In this case, it's -5, which gives us the positive value 5. Okay. And then we move on to more properties of nth roots. If a is positive real number and n is even, then a has exactly two real nth roots, okay? 2 real nth roots, which are denoted by this positive n square root a. So let's see if I can get a positive there. Positive n square root a, and then this negative, actually, rather, it's positive right out front. So, and then this negative square root of a. Okay, so for something like 81, if we're taking the square root of 81, we know that it will have two solutions, because 9 times 9 gives us 81, and -9 times -9 also gives us 81, okay? And then if a is any real number and n is odd, then a only has one real nth root, okay? Which is again denoted by this notation. So for 27, the cubic root would be 3, and then for the cubic root of -64, it's -4, okay? But if a is even, if n is even, so if n is even and a is a negative number, then we end up with a non-real solution, okay? And there actually is a solution to this, but we'll talk about it later. It's called a complex solution, okay? Later on in this chapter, we'll be going over that. And so now we move over to rewriting our old definition, right, that we saw in the principal nth root of a number to an inverse power, okay? So if I had the cubic root of 27, I could rewrite that as 27 raised to the 1/3 power, okay? Which again is still 3, okay? And the reason why this is more helpful is because we can take some number a and raise it to the power of some fraction, alright? So if I had 2 raised to the power of 5/5, not 5/5, but 5 halves. 5 halves instead. 5 halves. Okay, that would look like the square root of 2 raised to the 5th power. Okay, and the definition here goes through that type of formulation. So you can see that what I've underlined here and here are exactly the same thing. It's just all about which operation you would rather do first, and in some cases one is more useful than the other. So it's just a preference type of deal. And then finally we have summary rules for exponents. So if we have the same base, a raised to some power r times a raised to some power s, we add the exponents together, okay? And if we're dividing, we subtract the powers, and then if we're multiplying, right, we can distribute the exponent to each of our numbers. And if we have some number a raised to the power r, which is then raised to the power s, we multiply our exponents, okay? We multiply them. So that's the difference there. And if we're dividing two numbers that are both raised to the same power, we again just distribute the power to each of those numbers. And one of the easiest definitions is some number raised to the 0 power. That's always 1, okay? And so you can see right here, with this 3x raised to the 0 power, that's, if I can write that here, so we would have, whoops, let me fix that. We have 3 raised to the 0 power times x raised to the 0 power, okay? And I'm able to do this because I'm using my power rule right here, okay? And so 3 raised to the 0 power is 1, x raised to the 0 power is 1, so 1 times 1 is 1, okay? And then number 7 here, or our definition number 7 here, if we have some number a raised to the negative exponent, well, we have to take the inverse of that, okay? So if and I'll write it over here, if I have 3 raised to the power of 1, well, let's see, raised to the negative 2, okay, I would rewrite that as 1 over 3 squared, which is 1/9, right? And then finally, if we're dividing two numbers that are raised to the some negative exponent, we simply take the inverse, okay? And we saw how the algebra works for that last time. But now what we want to look at is our numbers where they don't fall on our multiplication table or anything, and they're much more tedious and laborious to do by hand. So if I had like the 4th root, okay, of 3.45679, okay, and say it just goes on and on. Doing this by hand would I don't know. I mean, I would want to say it would take you just a very, very long time. It's not impossible, but it would take you a very, very long time. So instead what we do is that we use a calculator instead. So what I'm going to do, I'm going to switch to that. Okay, and the calculator I'm using is just one that I Googled online. It's provided by NumWorks here. So if I wanted to find out what the solution to my radical here is, right, I would need to take the let's see, I'm going to put in 3.45679, and then I'm going to hit this button right here, and then I'm going to rewrite my 4th root as a fraction instead, okay? So that's 1 divided by 4, and I'm going to have to go over here, and then, so this will be taking the 4th root of this number a, okay? And I hit enter, and I end up getting 1.363554, okay? I'm sure it goes on, but it stops at a certain amount of decimal places. So if we wanted to see just a few more definitions in action, so if I were to do, let's see, if I had 5 divided by 2, okay, and then I raise that to the power of -5, what would I get? So we know how the algebra works, and what I'll do is that I'll switch back to Paint here and then write out how the algebra will work for that, right? So it may be helpful for you to just to look at your table here and see which definition we're actually going to employ, okay? I'll give you a second to think about that. Okay, so hopefully you should have guessed that we're going to be using rule number 8 right here, okay? And the reason for that is that because we have a negative exponent, right? So we can just take the inverse to make it positive. So it was the -5, yeah. And we flip our two numbers. Oops, let me fix that 5. Raised to the 5th. And then we can go and use definition 5 right here to distribute the power, okay? And this is the type of algebra that's expected of you. Certainly you could evaluate 2 to the 5th, but 5 to the 5th would just take a little bit longer. So that's why instead we would use a calculator. But you wouldn't use a calculator when you're at this step. Okay? You want to use it when you've gone down to here at least, okay? So if we switch back to our online calculator, we can see what that will give us. So all I have to do now is just hit enter, and we see that we end up with the fraction 32 over 3,125. Okay, so that's kind of why we start to use a calculator instead, is because especially as you get higher up in mathematics, you'll be dealing more with natural numbers, I suppose, or numbers that you would see in nature. And large and unusual numbers like that are kind of what you can expect. So if we look just one more time at one of our other summary rules here, if I were to take some number 5 times, actually let me go back on that. If we did 5 raised to the 3rd power, okay, 5 raised to the 3rd power, and then multiplied that with 5 raised to the 8th power, okay. So the parentheses here aren't necessary. Let me just get rid of those. But it doesn't matter if you included them or not. They would be necessary, however, if we were dealing with another type of operation like addition or subtraction. But because we're just multiplying two numbers, the parentheses aren't necessary because we know our order of operations. Okay, so we have the same base here, right? So 5, and they're raised to different powers. So take a guess at. Actually, you probably don't have to take a guess. You can just look at your table, and you should notice that we just have to add the exponents together, right? So 3 plus 8 is 11. So I could just back out of this and put in 5 raised to the 11th power, and I'll get this ridiculous number here. So if I did do 5 raised to the 3rd times 5 raised to the 8th, I should get the same thing. And voila, I do. So that's how we use the calculator. Whatever type of calculator you have, it should have similar buttons. And I can use the square root. I haven't used that function yet, so let me see if I can figure that out. I can take the square root of some number, right? So 81 gives me 9, right? But we know that we have a second root, right? So I can put out that negative sign right there, because because n is positive, right? And a is a positive number as well. So I should have two solutions, right? And so 9 and negative 9 are my solutions. If I wanted to try, I don't know if this calculator allows me to. I don't think it does, but just remember if I'm taking the square root of a number larger than 2, I can always inverse it. So again, if I wanted the cubic root of 5, the inverse of that is 5 raised to the 1/3 power, okay? Oh yeah, okay, so that's cool. It shows me right there. So the cubic root of 5, right? It rewrites it right there for me. So okay, next time we will be finishing up this section with radical functions, and what that's going to do is that it's going to take everything that we've learned and allow us to graph radical functions and find information about their domain, you know, where they're real at, and how we go about solving them. Okay, see you next time.